Hi guys, today we're going to go ahead and finish up Unit 5. Actually, we've done sections 1, 2, and 3. Those were actually the long sections with most of the stuff that we needed to know. All of these other sections, 5.4 all the way through 5.11, they're all very short. So we're just going to finish up Unit 5 today with all of our notes so that we can come back to class and get a bunch of practice in over the next couple days before we finish up. So let's go ahead and get started. Okay, so far we've been looking at just overall reactions and figuring out what the order of the reaction is, what the rate law equation is for the reaction, the overall reaction. But what really happens is that reactions take place in a series of steps. And those series of steps, each one of those steps in the series is called an elementary reaction. And so today we're going to look at those individual steps and characteristics of those individual steps, how we can use those to figure out rate laws and learn some stuff about the reactions. So if we're looking at a series of steps, so normally what will happen is they'll give you an overall reaction, and then they'll tell you what it is, and then they'll tell you, okay, these are the steps that take place. Step 1, step 2, and then, maybe if there's multiple steps. So it'll show you all the different steps of the reaction. Each one of those steps is an elementary reaction, and we're going to be analyzing those. So each one of these elementary steps forms a new substance in a single step. So elementary reactions can be what are called unimolecular, bimolecular, or trimolecular. And that just is really based on how many reactants there are. If there's only one reactant, then it would be unimolecular. And if we write the rate law of a unimolecular step, what we can do, so the rate law right here, the rate law of an elementary reaction can be determined from the coefficients. And those coefficients are going to become the exponents in our rate law. So if this is my unimolecular step here, O3 gives me O2 plus O, rate is going to be equal to K times the concentration of O3. Since the coefficient is 1, then my exponent here will become 1. So when we're writing rate laws for elementary steps, which are just individual steps in an overall reaction, we can take those coefficients and turn them into the exponents. That's only if you're given all of the steps of the reaction. Bimolecular elementary reactions have two substances turning into products. So the rate law here would be rate equals K times NO. We're just going to take each of our reactants here and take those coefficients and turn them into our exponents. Trimolecular, also called termolecular, is when we have 3 reactants. The rate law here would be K times NO squared because of this coefficient right here, and then times O2. So we can just take our elementary steps there, take our coefficients, turn them into exponents for rate laws for the individual steps. We cannot do that for the overall reaction, just for the individual steps only. Okay, this next section we've talked about before. In order for any reaction to take place at all, 3 things need to happen. First of all, the molecules need to collide. They need to collide with enough energy. That amount of energy is called the activation energy. Okay, so we've talked about that before. And they also need to have the proper orientation, which means that they need to collide in the right place. If they don't collide in the right place, then bonds don't break, new bonds can't form, and then you don't have a reaction that can take place. We've seen this graph before. Remember, this is our Maxwell-Boltzmann distribution. So this is a good review of this. This is from Unit 3. If we have 2 graphs here that we can compare their different temperatures. So remember, this one right here would be our higher temperature. And it would be our higher temperature because remember, our peak kind of represents that average velocity where most of our molecules have that speed. And so this is going to be faster moving molecules are going to have the peaks over to the right. Slower moving molecules are going to have peaks over to the left. And what we need to know here is the area under the curve. We did talk about this before. This is just a good review as it relates to this unit. The area under the curve past my activation energy line represents my number of molecules with enough energy to react. So if I have a molecule or molecules that are at higher temperatures and the area under the curve is even greater, then that means you're going to have more molecules with enough energy to react. Because the area underneath the curve is greater. Okay, we need to understand some stuff about energy profile graphs. So with any reaction that's taking place, whether it's, all of the elementary steps, all the steps in an overall reaction, we have bonds that are being broken, we have bonds that are being formed, and all of those bonds store a certain amount of energy. So we have these energy profile graphs that show us, in this particular case right here, shows me how much energy my reactants have and how much energy my products have. So what you can notice from this graph is that my product energy is lower than my reactant energy. So what that means is that in this particular reaction, energy is lost or energy is released. And if energy is released or lost, then that is an exothermic reaction. Okay, also notice that there is this little peak right here. That little distance from the amount of energy that the reactants have to the amount of energy it needs, the transition state is how much energy it needs in order for the reaction to begin. So this represents my activation energy. So this is my exothermic graph. If it is an endothermic reaction, one that absorbs energy, then our reactants are going to have energy down here, and it's going to go up, absorb a certain amount of energy, and my products are going to have more energy than my reactants. This is going to be an endothermic process when energy is being absorbed from reactants to products. My activation energy here on this graph is going to be represented from the energy of my reactants all the way to that transition state where the reaction is able to begin. Okay, in this next section, this equation is actually not one that you ever need to do any calculation with, but you need to just be familiar with it if you see it. They'll give it to you and you just need to know what everything represents. So EA represents our activation energy, and T is temperature, R is a constant, A and then E, those are constants. K is our rate constant. So all you need to know about this equation is it shows the relationship between our rate constant K, our activation energy, and temperature. What it shows us is that K is going to increase as the temperature increases, but K is going to decrease as activation energy increases. Over here on the right side, there's some kind of calculus stuff here that is done. Basically, what you need to know there is if you have a graph that has the natural log of K on the y-axis, 1 over the temperature on the x-axis, the slope of that graph is going to give you your activation energy over R. So if you take your slope of this graph times R, it will give you the activation energy. So activation energy can be calculated that way. Again, you'll never be able to actually, or you're never going to be asked to actually use this equation, but just understanding what's going on there is important, understanding the different parts of the equation, what they represent. All right, what we're going to go through on this slide is actually the biggest part of this section of Unit 5, talking about those reaction mechanisms. When you're actually given those things, what do you do with them? How do you figure out what's going on there? How do you figure out the overall reaction? And then also figuring out something that are called intermediates and catalysts. So the reaction mechanism gives us the series of steps that take place in order for an overall reaction to happen. And there are reactants, there are products, there are intermediates, there are catalysts. So let's just take a look at this example that's down here at the bottom. If I go ahead and combine these two equations together and add them together, basically, I'm going to have, I've got two H2O2s over on the left side. And let's see, I've got an OI minus on the right and I have an OI minus on the left. And I'm comparing everything to where these arrows are. So if I have one on the left and I have one on the right, then they're going to go ahead and cancel. I also have an I minus on the left and an I minus on the right. So those are going to cancel. What I'm going to go ahead and get on the right side of my arrow is going to be 2H2O and then O2. And all of the other things cancel. So my overall reaction is going to be 2H2O2 gives me 2H2O plus O2. This is my overall reaction based on the series of steps. Now what I need to know is which one is the intermediate, which one is the catalyst. So intermediates are produced in the first step and used up in the second step. So produced in the first step, used up in the second step. This is going to be my intermediate. It's an intermediate product. And then my catalyst is going to be a reactant in step one and a product in a later step. So reactant in step one, product in a later step. This is going to be my catalyst. So catalysts are always present at the beginning of the reaction and also at the end of the reaction. So you have to be able to look at those series of steps and identify what are the intermediates, what are the catalysts, and what is the overall reaction. So we're going to be asked to take a look at a reaction mechanism like the one that's down here. So we have this overall reaction, W plus Y gives me Z, and it says it has the following sequence of elementary steps, which is the same thing as saying reaction mechanism. We're going to be asked to use the reaction mechanism to figure out what is the rate law equation. And what we want to look at is we want to look at the rate law. Let's see, this section right here is determined by the reactants and coefficients of the slow step or rate determining step. So if you're given a series of steps, you want to find the slow rate determining step. And when you do, you're going to take that reaction and we're going to write rate equals K times, and then we're going to use that reactant of our rate determining step, put that in here. Our coefficient, which is a 1, is going to be our exponent. The only time we can use coefficients as exponents is going to be when we are given reaction mechanisms. And so my rate law for this reaction, so this is what you're going to do if you're not given information to do rate laws like we did in the first section of Unit 5. If you are given reaction mechanism information, then you're going to use that rate determining step to figure out the rate law equation. Okay, another type of question that we're going to see with reaction mechanisms is going to be one where we're given a rate law and an overall reaction and then a suggested mechanism. And we're going to be asked, does this mechanism match the overall reaction? Now, first of all, and does it match the rate law? First of all, there's a little bit of a typo here. This rate law doesn't match anything that's here. So let's rewrite one. Let's write a rate law of rate equals K times NO2 squared and then times F2. Another typo is going to be, sorry about this, in step number 1, there should also be plus F over on the right side. Okay, so in order to figure out if this reaction mechanism is a reasonable reaction mechanism, we have to check two things. So the first thing we have to check is we have to check and figure out what the overall reaction is based on this reaction mechanism. So overall reaction here, I have an F on the right and F on the left, so those are going to cancel. What I end up with is 2NO2 plus F2 gives me 2NO2F. And what I want to do is I want to check Does this match the overall reaction that's given to me in the problem? If it does, then that's going to meet the first criteria. The second thing I want to do is I want to look at the slow step, and I want to figure out what is the rate law based on that slow step. Now remember, we take our reactants and take the coefficients and make them our exponents. So this is going to be, sorry, I forgot the K, NO2 to the first power, and then F2 to the first power. So I want to look at these exponents and see, do they match these exponents? And if they do, then yes, this is a good reaction mechanism. In this case, you can see that it doesn't match. So really, the answer to this question, it's really just a yes or no question. Is the reaction mechanism consistent with the experimentally determined rate law? The answer is no, and the reason is that the rate law equation from your rate determining step doesn't match the rate law that we know to be true for that particular reaction. So that's not a good reaction mechanism for that overall reaction. We're also going to see reaction mechanisms where we have this double arrow situation. That's really, really important to pay attention to. If you have a reversible reaction, then what happens is it basically means that these two things are interchangeable with each other. And so if you have A, then you also have X. It means that the reaction is going back and forth all the time. And so if I want to write the rate law for my slow rate determining step, I can go ahead and take A and I can substitute in for X in my rate determining step. So what that means is instead of X right here, I can go ahead and I can substitute in A. So if I want to go ahead and write the rate law equation for this step, it would be rate equals K times A times B. So anytime you guys see that double arrow, that always means that you're going to be substituting in for a different part of the equation. That takes care of the fact that X, which you should notice, X is an intermediate. So that's going to take care of the fact that we don't want intermediates in our overall rate law. We will also see questions where we'll be given, here's our overall reaction, and we are given our rate law. And then we're given two possible reaction mechanisms, and they're going to ask you which of the following reaction mechanisms is a better choice or is consistent with the rate law that's given. So all we want to do is we want to take a look at those slow steps, figure out what those rate laws would be from those slow steps. So here I would have, actually, if I write my rate law from this slow step, rate equals K times ClO2 times F2. But the problem is I have this double arrow. So if I have ClO2 F2, that means that I can go ahead and substitute in these substances. So that really is a rate law of K times ClO2 times F2. Okay, so that actually, if you look at that right now, does match the rate law that's given to me from the experimental data. So if it matches, then that's the correct rate law. So we're going to choose, or I'm sorry, that's the correct reaction mechanism. We're going to choose reaction mechanism number 1 as the correct reaction mechanism. Let's just go ahead and confirm that with the rate law from the second set of steps. This rate determining step or slow step would give me rate equals K times F2. And this does not match at all, so that would not be the correct reaction mechanism there. Okay, we're getting close to finishing here. Let's take a look at this energy diagram. We looked at the endothermic and exothermic graphs. If you're dealing with a reaction mechanism where you have different steps, step 1, step 2, then there will be 2 different energy diagrams. You can see like this blue section would represent step 1, this green section would represent step 2, and they would connect in the middle. In the middle would be the energy of our intermediates, At the beginning on the left side would be the energy of our reactants, and then on the right side would be the energy of our products. And so different steps can be endothermic and exothermic. So this might look a little bit different depending on which step is endothermic and which one is exothermic. But as long as you know that in the middle here represents the energy of our intermediate products, that these peaks represent the activation energies of the different steps. So anytime you have multiple step reactions, if you had a third step, then you would have a third graph that would show a different intermediate, different product, and so on. So we know that catalysts speed up reactions. They speed up reactions, but they are not consumed. That's why we always see them at the beginning of the first reaction and at the end of the second reaction. That's always where a catalyst position is going to be, remains unchanged. All it does is it speeds up the reaction because it changes the series of steps that takes place, and it gives a series of steps that will happen a lot faster, increases the number of collisions that are effective or able to react. If we're looking at our Maxwell-Boltzmann diagram, like how we looked at before, then basically that activation energy line is just going to be moving farther to the left, and that's going to give you more molecules that have enough energy to react and collide and create new bonds. A really common question on the AP exam, you guys, is to take a look at an energy profile diagram where we have our reactants, our activation energy, and then our products. And it will ask you to draw what the curve will look like if a catalyst is used. So what's really important for you to notice is that my reactant energy, my product energy is the same no matter what. And the only thing that's different is the height of that catalyst line. So that yellow line that I drew represents the activation energy when a catalyst is used. The height of my blue line represents the activation energy without a catalyst. Also, things to know, delta H is also the same thing. You'll see delta E means the change in energy for the reaction. That it is going to be the difference between the reactant energy and the product energy. That's going to be this distance right here. So you guys will be asked to sketch energy diagrams. Take a look at this. So we are going to draw an energy diagram for a reaction in which the reactants have an energy of 300 kilojoules and the energy of the products are 700 kilojoules, and the activated complex is 800 kilojoules. The activated complex is just the peak of the graph. So what's going to happen is it's going to start at 300, go all the way up to where that peak is, and go down to where that product energy is. So my graph is going to look like this. We can go ahead and label reactants, products. It's also asking us to label the change in energy. So my change in energy is okay, sorry you guys, my computer went offline. So hopefully we are good to continue on here. Let's see, so this is gonna be my change in energy for the overall reaction. Notice that my reactants, I'm gonna be absorbing energy to turn into my products. That makes this an endothermic reaction because I'm absorbing energy. My products have a higher energy than my reactants. That means that also delta E is going to be positive. So that's going to be important to know. So we've labeled delta E. It also asks us to label our activation energy. So my activation energy is going to be right there. Nope, sorry. from my reactants to the peak of my graph. So that whole thing from 300 all the way up to 800 is going to be my activation energy. So activation energy is going to be 500 kilojoules right there. And then it'll say another type of question you'll see, what is the activation energy for the reverse reaction? Now, if it is the reverse reaction, then I'm starting right here at 700 and going up to 800. So that difference from 700 to 800 is 100 kilojoules. So my activation energy for the reverse reaction would be 100 kilojoules. And if a catalyst is used, I'm going to show my same reactant energy, same product energy, but my peak for that activation energy is not going to be as high. Last thing real quick are going to be the 3 different types of catalysts that you can be familiar with. You don't necessarily have to be able to identify them in like a reaction mechanism, but just kind of know what each one does. So acid-base catalysts, we know that acid-base reactions are all about hydrogen ions being transferred. Are they being gained? Are they being lost? If you see that transfer of hydrogen ions in the reaction somewhere, that's an acid-base catalyst. The other one you wouldn't be able to see from the reaction mechanism, but a surface catalyst is just one that binds to the surface of whatever the catalyst is, and it changes the way the reaction takes place. And so this is how a catalytic converter works in your car. So you have your platinum catalyst surface, and you have oxygen molecules that come in here, and when they bind to the surface of the platinum, it separates those 2 oxygen atoms, and those carbon monoxide molecules that are produced with the engine of your car can come in, bond to that extra oxygen, produce carbon dioxide, which is then released. So that's how carbon dioxide is released instead of carbon monoxide, is because of that platinum catalyst. So that is a type of surface catalyst. And a very common and important catalyst to us are going to be our biological catalysts, which are called enzymes. If you've taken AP Bio, then you've probably learned a lot about enzymes, but basically they're just biological catalysts that assist in different biological reactions, such as cellular respiration. Basically, we have these enzymes that have certain shapes, and then our substance comes in right here, and because of the shape of the enzyme and how it changes shape, it's able to allow different products to be formed and actually assist in the formation of those products. So those are enzymes, are biological catalysts. So those 3, we've got acid-base catalysts, surface catalysts, and enzymes as our biological catalysts. So you guys, we have finished with Unit 5, all about reaction mechanisms, energy profiles, catalysts. So when we come back to class next time, we're going to be doing lots of examples with looking at those reaction mechanisms, figuring out rate laws, figuring out which reaction mechanisms work for overall reactions. So lots of practice in class next time. So I will see you guys then. Have a good day.